Hello, everyone. Today, my talk is a modeling approach in student learning and appreciation of differential equations. So my name is Biyong from University of Massachusetts, Dartmouth. So today, first, it's my description of my talk. In the second part, I will introduce this course topic, schedule, and the embedded modeling application in this course. And next one is an example of projects. And last one is feedback and some students, their appreciation and my course evaluation. So first one, today I will share my decade-long teaching experience. Teaching this challenge differential equation course. As we know, many professors and students think differential equation course is the most difficult undergraduate math course. And also, I will share my detailed design of course material covering complex topics and the modeling approach. The engagement and the student support in and out of classroom is very important for students learning differential equation course, which will augment students' mathematical fluency and their appreciation of learning differential equation course. We know that, so this appreciation of the importance of differential equation course will enhance students' learning and their mathematical growth. Next one, I will show my expansive course objectives. This is like a typical course objective of differential equation course. First, we need the students understand the fundamental methods of differential equation course, quantitative analysis, and numerical methods in solving nonlinear differential equations, and to gain substantial understanding of mathematical modeling as with the ODEs. Except that one, we will provide an introduction to differential equations modeling and a natural critical learning environment to inspire students for deeper and broader understanding of mathematical modeling through in-depth class discussion and the embedded modeling differential equation course into the homework assignments and the projects in their relation to the course topic. So next one, I will show my course design for this contents. I use the Zill's textbook. It's called Differential Equations and Boundary Value Problems. For first chapter, 1, 2, 3, there's a typical one, right? It's a wide class of first order ODE and models, quantitative analysis, and numerical techniques. That's usually will spend 3.5 to 4 weeks. Next one is chapter 4 to 5. That's higher order linear equations. Units called with the constant coefficients, whether homogeneous or non-homogeneous, and the related models and quantitative analysis. Next, just chapter 8 to 10, it's a linear system of ODEs, either homogeneous or non-homogeneous models, and quantitative analysis for nonlinear system. Next one, we have chapter 6 and 7. That's called a, sorry for that. That's called a, power series solutions and Laplace transforms and initial value problems. So usually this one will put out at the end, and if time if time permits, we will cover power series solutions, but for sure, we will cover Laplace transforms and the initial value problems. So next one, we'll just list some like interesting projects or ODE applications related to first 3 chapters. So like typically we have this collection of simple modeling of population growth model, or call it chemistry, active decay or growth, and the interesting problem and the half-life with this kind of formula. It's like students could solve this kind of problem even from calculus 1 or 2. Next one, we'll do a modeling fixture of 2 solutions of different chemical concentrations. So this one just usually we have like a rate in, rate out problem. And next, I will show one project related to this kind of chemistry application problem. That's big project of this course. And the third one, it's like kind of a simple modeling spread of contagious disease. This is with a small community. So this model, it's like x prime equal kx times n plus 1 minus x, and start from a infection number with 1. Next, we have called a logistic model or the modified logistic model. You will combine these two together. So for this first factor, like a P divided by N minus 1, let's call it one population with the scarcity level N. And the second factor one, or this one should be P minus M. That's maybe maximum population size. So that should be corrected to M. Next one, we'll just show you that's chapter 8. So after students start chapter 8, like linear system of ODE, I will give them some kind of call it skills inventory exercise problem. Ask students to solve this problem, determine the value of C, then draw this corresponding like the solution curves, whether they could use an applet with many, free, or some of them could use an MATLAB or using other software. So students are encouraged to explain why they have such kind of graph, or explain the behavior of each kind of graph related to different value of C. Next one, we'll do the kind of modeling application problem. So this will talk about say, students know this 2 species population model, whether they have like this problem, they will ask students based on their knowledge to determine which of the following term basically describe this above model, whether this predictor prey or competing species or cooperating species. So this one, sometime we know that if this is a different like parameter with the first equation, like xy with different parameter in first equation, and in second equation, they will describe the different model. So this one here, we just give students one simple this kind of model. And the next one, in next example, they will give the different parameter for this in these 2 equations. So for number B, they will usually ask students find, this is like a typical ODE problem. Find the critical points and the corresponding linear system, and then classify each linear point as either stable or unstable, and using slope field applet. I will use one free software. Let students choose the best one or software to check their answer for this above problem. That's like here. Next problem, we just ask students to use kind of software to determine the different alpha, the parameter, and related to this model. So this is a given students, this is a predator and pre-system, and later on students will describe the limited behavior of x and y as t go to infinite, and interpret the answer in population of two this competitive species. So that's a typical embedded ODE application in the course to each chapter. Of course, we have many website. We use a website, using Cengage website. We have a lot of application problem, except that application homework problem. I give students some kind of example of projects, ask like them to work in a small group with 3 or 4 students to work on these 2 projects. First one is modeling complicated pollution problem. This one just related to chemistry, first one we introduced that one called rate in and the rate out problem. So students could follow the assignment actually to solve first part of this problem, like give this kind of call it non-statement problem. Students translate this mathematical information into a ODE model, and I believe your students could do the first part as well. So do you have a question about this project? So if no question, so second part, we're asking students to work on part 2. The part 2 actually, it's not very difficult because the homework have the similar problem. Like when the union just said that when they let's say some like some call it say pollution in that tank reach certain level, then the administrator will turn off the outside input, and then using the fresh water to clean the tank. So generally, that's the part 2. So this one just asks students to work on this in small group and to relate this project to public policy. So this one just give students the exact solution. Of course, some group could reach this kind of accurate level. Some group maybe not reach this kind of accomplishment. So that's first project. So next project is called a logistic population model with a harvest. So this we did this like kind of problem given in chapter 2 for the 2.1 called ask students sketch solution curve. that time we ask students just use software or applet to first translate this model to mathematical equation, ODE equation, and that time they could solve the mathematical strictly get the exact solution, but many of them maybe not reach that level, but they at least could use that software applet to have this kind of graph. They could explain the long-run behavior of this solution. But the problem is, we'll ask them to go to deeper studying. It's called how the like harvest level equal 15 when the fish population are to this two critical number, like 250 and 750. So that's challenge for them. This one just like a proof for students to get the ideal harvest level. So last one is the outcome and the course evaluation. So outcome of students' feedback or to this course is very impressive. So many students even just express their deep appreciation of the class, how the class provides the solid foundation for their future studying or for their other course or even go to graduate school. My shared experience here, just like say, we need a highly detailed approach to planning and teaching, especially you using some like very effective or innovative assignments or projects or in-depth class discussion or that example or hands-on homework problem to allow students to start and grow in an immersive in learning atmosphere. So they emphasize on how different equations modeling can be applied to real-world problem or enhance students' learning and their appreciation of differential equations. So that's my talk today. So next one, welcome you, everyone ask questions.
Thank you so much for this talk. It was fantastic.